Good morning, class. Today we're going to continue with some more examples of what to do with connected masses. So what we have here in our first example actually looks very similar to the examples that we were doing in our last set of notes. We have our 5 kilogram block tied to a 10 kilogram block. The 10 kilogram block is placed on a table and the 5 kilogram block is hung off the edge. What's different about this one from what we did before is now the table has friction. We see it has a coefficient of friction of 0.1. Well, with that being the case, we now have a new set of forces for us to consider. So our first step should be to draw in a free body diagram or draw in all the forces. The first thing I'm going to do is I'm going to give each of my masses a name. I'm going to call this Alfonso and this one Bartholomew, or mass A and mass B. What are the forces on these now? Well, I know Alfonso has some gravity, but also Bartholomew does as well. Taking a look, I see that mass A is sitting on a surface. If it's sitting on a surface, that means there's some normal force occurring here. Mass B is not on a surface. There is no normal force there. Additionally, there's going to be some friction resisting this motion on A because there's friction on that table. Mass B is not in contact with anything, so we have no friction again. And lastly, we have ourselves a little bit of tension, but as we've discussed before, internal forces like tension are not going to be something for us to consider when there's the motion of the whole system. Now, how do we solve this? How do we determine the acceleration of the whole system? First thing we need to figure out is what direction will things be moving? I can see that the most likely situation is that the 5 kilogram block gets pulled down by gravity, and that's going to pull the 10 kilogram block to the right. It seems that my direction of motion is kind of like this. Notice how it bends as it gets to that pulley. So saying up, down, left, right doesn't work because my direction of motion bends depending upon where in the system you are. So I'm no longer going to use left, right, up, or down as my direction. I'm going to use my winning direction, and I'm going to use my losing direction. Winning, I'll say, is plus. Losing, I'll say, is minus. This means now I can make a net force equation for all of my forces that are in the direction of motion. Which forces are in the direction of motion? Well, I see these forces are, when I'm looking at mass B, but when I'm looking at mass A, it's these forces. Who haven't I highlighted? I haven't highlighted force gravity A, nor have I highlighted force normal B. These forces balance out. They do not cause any change in motion to the whole system. So I get to ignore these. Now I'm not going to totally cross them out. They may be useful later. One more thing for us to ignore. Remember how we said tensions are internal forces? They cancel out. They do not count when we look at the entire system. We will do more examples looking at tension in our next video. So let's go ahead and see, what are my winning direction forces? It looks like force gravity B is moving in the winning direction. And of my highlighted forces, which ones are in the losing direction? It looks like it's the force of friction from A. Can we solve any of these right away? Well, force gravity B actually is pretty easy. It's going to be 5 times 9.8, or that's 49. So I get to plug in 49 for force gravity B right away. I want to determine the acceleration. I don't know it. Now, we know this is mass times acceleration. What masses are being pulled? Both the 5 kilogram mass and the 10 kilogram mass. So that's a total of 15, right? Because both of them are being pulled, so I'm going to include both masses. The only thing that we haven't done here is the force of friction of A. Do we know what the force of friction of A is? Oh, not right now. We're going to have to spend a little bit of time trying to figure out what is this force of friction of A. Well, the formula that we have for force of friction is the coefficient of friction multiplied by the relevant normal force, or in this case, it'd be the normal force on object A. We don't have a number for the normal force on object A, but we noticed that it's balancing gravity in this particular situation. So gravity being 10 times 9.8 for object A, being 98, would balance our normal force, meaning our normal force is the size of 98. Our coefficient is 0.1. Our normal force is 98. This means our force of friction A is going to be 9.8 newtons. 9.8 newtons. Now that's good. We can solve this. That's because we have all of the numbers for everything except for that acceleration. So we have 15 times A is going to be equal to, that'd be 39.2. And to get the acceleration all on its own, you want to do the opposite of what's happening to it. Being multiplied by 15 means you should divide both sides by 15. And your acceleration here is now solvable with a little bit of a calculator. So that's 2.61 meters per second squared. And the direction of motion is in the winning direction, so it's just a positive. Okay, let's look at our second example. A 15 kilogram block is tied with a rope to a 22 kilogram block, and the blocks are placed on an Atwood machine, which is a pulley that lets both masses be suspended in the air. Let's assume the pulley is frictionless, and let's determine the acceleration of the system. All right, let's draw our situation out. So this is what an Atwood machine would look like. We have a pulley here, and we have two masses on either end. To solve for the acceleration of the system, we have to make a net force for each one. I'm going to call this again object A, and I'm going to call this one object B. What forces are there? Well, there's some force of gravity from A, and there's also some force of gravity from B. Now they're both heading down. Does that mean they should add together because they're working together? Hopefully, in that pause, you just said no. When you pull the 22 kilogram mass down, the 15 kilogram mass would go up. Clearly, those forces of gravity are working against each other. I hope you were able to recognize that. So this means that when we make our direction of motion, the direction of motion actually does a 180, like you see here. And our winning direction is going down on the right side, up on the left side, and our losing direction is going down on the left side and up on the right side. We can use this to make our net force equation. My net force equation would be all of my winning forces, force of gravity of B, minus all of my losing forces, the force of gravity of A. Take a moment and try to finish this problem on your own. So let's determine, we want to know the acceleration of the system, so we need to know the mass of the system. There's 15 plus 22 times A equals force of gravity B. We need to take 22 times 9.8, 215.6. And we need to find the force of gravity of A. That's 15 times 9.8, 147. So take a moment to finish things up in your calculator to tidy up and do the algebra to solve for the acceleration. hopefully you find that you would solve for 1.85 meters per second squared is our acceleration, and it is positive because it's in the winning direction, and I have shown my winning direction right here. So since I've drawn out my winning direction, I can just leave it as a plus sign. All right, that's all for today. We are going to try more examples tomorrow. Have a good day.